And next speaker is Bak Nielsen with another Super-Eddington source.
Okay. Hi. I'm a PhD student at Leiden Observatory. And I'm going to tell you a little bit about why we think that this source, 2A1822-371, might be a Super-Eddington source. I'm going to start by leaving you with my conclusions, actually, because it's also the outline of my talk. I'm going to start by going through why we think that we never see the surface of the neutron star, why we think that that we have to have an optically thin or not very opaque accretion disk corona. Then I'm going to show you the long-term and short-term spin-up. And then I will move on to why we think it's a Super-Eddington source with probably a low magnetic field. And then if I have time, I will show you some comparisons to some other sources. But first of all, let's meet the system. So it's a low-mass X-ray binary. It's a persistent X-ray source. The Pulsar has a spin frequency of about 1.7 hertz, which is about 0.6 seconds. The luminosity is observed to be about 10 to the 36 ergs per second. And interestingly enough, we find an X-ray to optical luminosity of about 20 to 60, which is quite a lot lower than what you would normally expect. Usually you would expect something like a few hundreds to 1,000s. But we do see the source edge on, so that might explain some of it. It has an orbital period of about 6 hours and an orbital period derivative of about 2 times 10 to the minus 10 seconds a second, which means that the two sources are moving away from each other quite fast. And then there are two claims for a magnetic field of the source. One is about 10 to the 10 Gauss, about 10 to the 10, 10 to the 11 Gauss. Which is from the group of Yari et al. And the other claim is for about 10 to the 12 Gauss from Sassano et al. And both of these claims are from cyclotron resonance scattering features at 0.7 or 30 keV. So two quite different claims, and I'll come back to that as well. We have used RxTE data over a baseline of about 13 years, from 1998 to 2011. And now I will move on to the light curve and to why we don't think we see the pulsar surface, neutron star surface. So the light curve is quite interesting. It's an accretion disk corona source, an eclipsing low-mass X-ray binary. So we see this is the eclipse, but the only part that's really not eclipsed at all appears to be around here. It's only a semi-eclipsing source. It only goes down to about half of the maximum counts. And it's thought to be an accretion disk corona source because it has these very wide sort of eclipses, very wide regions in the light curve. So we think, so it's proposed that there needs to be some sort of X-ray emitting region around the source to give these very wide features, but still only be eclipsed about 50%. So because of this light curve and because it's only eclipsed about 50%, so we always have some sort of emitting region, we were wondering if we ever see the surface of the neutron star. So we looked at the fractional amplitude for eclipsed parts. So just for the sake of argument, we defined the eclipsed parts as the entire part here, and the non-eclipsed as being the small part that has the highest count rate. So we looked at eclipsed data and the fractional amplitude of non-eclipsed data, and we see that there's not really any change over the orbital period, which means that we most likely never see the surface, but the pulsations that we do see comes from this X-ray emitting region. So all the light that we see is through this region. So then we can have a look at this region, which is the accretion disk corona. So it's proposed to be some sort of extended X-ray emitting region around the accretion disk. It would look something similar to this figure if we saw it from the side. And the inclination angle for the system is quite high. It's about 83 degrees, so we really are seeing it from the side. And the accretion disk corona is consisting of some sort of evaporated material from the accretion disk. But this made us wonder, because usually when you see the spectrum, and people fit the spectrum, this is the spectrum of the source, by the way, it's fitted with a model that has very opaque, that seems to be very opaque, or that seems to take into account that the accretion disk corona is very optically thick. But that does leave us with a bit of a problem, because if we have a very thick corona, we wouldn't be able to see pulsations. And we do observe coherent pulsations. So we wanted to try and see if it's possible to create the same shape as the spectrum that we see. So we took the best fit to the spectrum. It's a proof of concept. So we took the best fit to the spectrum, which is the red line. And we tried to upscatter it through an inverse Compton upscattering code, which is created by Giannis and Sprout in 2004, to see if we could have an optically thin corona. So instead of about a tau of like 10 to 20, we set the tau to be equal to 1, which should be thin enough that you can still see coherent pulsations. And the blue curve is sort of the model spectrum, and the black curve is what we find after we send it through this Compton upscattering code, which gives us a spectrum that is similar in shape to what we see in reality. So let's move on to the spin-up of the source. We have 13 years of data from RxTE. So we found the spin of the source in all of these data, and we find an overall spin frequency derivative of about 7.6 or 8 times 10 to the minus 12 hertz per second, which is a fairly fast spin-up. It does give us a spin-up time scale of about a few thousand years, which is quite fast. And we see some variations here and there, and because it's quite a fast spin-up timescale, we were wondering if there are any changes on a smaller timescale than just the overall long timescale. So we looked at two different segments of data that we could phase connect, one in 2001 and another set of data in 2002. And we saw that in the phase-connected data, if we don't take a spin frequency derivative into account, we see this very clear parabolic shape, which is a clear sign that there is a spin frequency derivative. And we find in these two segments spin frequency derivatives that correspond to the overall long-term spin frequency. So our source really is spinning up. So we were wondering, well, is there some explanation for this? And we compared it to some other sources. One is 4U1626 minus 67, and another could be GX1 plus 4, which both show a very fast spin-up. And then after a while, it spins down at about the same spin-up, spin-down timescale. This is one possible future for this source. However, this might not be the only possible future or idea for what is actually going on in this source, because we can also look at it as a Super-Eddington source. So there are some problems with just what we just found and the normal assumptions that you make about this source. And that is, for instance, that the orbital period derivative cannot be explained. So the change in orbital period, you can't explain that by a normal conservative mass transfer. So we're wondering if we can do this by assuming that it's somehow out of equilibrium, that it's transferring mass on a different time scale. And here we say that it's actually transferring mass on a thermal time scale, which would be a time scale about 10 to the 7 years. And that would give us a mass transfer rate of about 10 to the minus 7 solar masses per year, which is Super-Eddington. The Eddington limit is about 10 to the minus 8 solar masses per year. So we started by looking into if this mass transfer rate, this higher mass transfer rate, could explain the orbital period derivative. And we looked at the A dot over A, which is dependent on the mass transfer rate, and compared it to the orbital period derivative. And we find that to within an order of magnitude, it fits. So a Super-Eddington accretion rate could actually explain the orbital period derivative. So to see if this seems reasonable in other parameters, we looked at the King-Lesotho model from 2016 that Yuri Potanin also mentioned, where they look at the ULX M82X2 to see if it fits in the sort of general idea of ULXs as beamed X-ray sources with low magnetic fields, as Yuri just explained. And they estimate the magnetic field from the magnetospheric radius and the spherization radius. So we try and do the same, and we find a spherization radius of about 10 to the 7 centimeters and a magnetospheric radius of about 10 to the 6, 10 to the 7 centimeters, so approximately around the same, and a magnetic field of about 10 to the 10 Gauss, which is a bit lower than what you normally expect for the low mass X-ray binaries. But it sort of corresponds to what Iaria et al. In 2015 proposed for this source. And this, for us, would mean that we have a geometry of the source that's similar, that looks somewhat like this. So we have the neutron star in the center, and we have some sort of beamed region. And then because our magnetospheric radius and our spherization radius is about the same, the inner disk would be puffed up. And then we would have this outflow or accretion disk corona around the thin disk still. And then the magnetic field would still be low, but with some sort of beaming. We can actually test some of these things. We could look at a new star observation. So we can test if the magnetic field is about 10 to the 10, 10 to the 11 Gauss, or if it really is the claim of 10 to the 12 Gauss that's correct. By looking with new star at around 30 keV, new star should be perfect for that, and seeing if we can find a cyclotron resonance scattering feature there. If we do not, it's possibly a stronger claim for the 10 to the 10 Gauss field. Also, if this is the case, it should not be similar to the two other sources that I mentioned, to GX1 plus 4 and 4U1626. We should not be able to see torque reversal. And we would probably have some sort of jet or outflow present in radio. And we could also look at that. And there's not really any observations in radio for this source. So that's a clear possibility. We can compare this to some other sources. For instance, SS433 has a somewhat similar geometry. It's a black hole and not a neutron star. But we still see the inner disk being puffed up, and we see some sort of outflow. And I think the source is suggested to be ULX or a possible ULX. We can also compare it to some of the other accretion disk corona sources. For instance, for U1624 or AC 211, you see the same sort of light curves, so some of the same features. You only have the sort of 50% eclipsed. Of course, you see these things. You can also compare some of the spectra from these sources. So this is the spectrum for 21822, and we see that it has this sort of cutoff around 10 keV, which also two other accretion disk corona sources show. However, not all of the accretion disk corona sources show this cutoff, or at least we're not sure, because some of these sources have quite limited data. But we think that it might be a Super-Eddington source. And then I will just leave you with my conclusions. Thank you.
Thank you. Questions?